Hello, tensor friends. If the videos ago, we derived a generalized expression for the gradient of a scalar of the field that works in any the coordinate the system. So this is a proper tensor equation. Now we want to find the generalized equation of the divergence of a vector, the field. Okay, and this is called the Voss-Weil formula, and it looks like this. So we've been working on the metric determinant. So you see it shows up here. That's why we did that first, because I needed to understand what that was. All right. So let's just quickly review what is the divergence in Cartesian coordinates. Let's re-investigate this. So we got the del operator dotted with a vector field. So this is the del operator in vector form. And here is our vector, components and basis vectors. So when we dot these together, remember the rules. Ex dot ex is 1. Ex dot anything else is 0. Likewise for the others. So you just wind up with this expression, which is a scalar field, right? Okay, now we can generalize that by just saying the partial with respect to an arbitrary, the coordinate of the vector component. But look at this. We've got I and I here. So we've got a full contraction. So that ensures this is a scalar field. Now, how can we change this to a proper tensor equation? Well, the first thing to try is put in the covariant derivative. And notice that it has an I and an I. So this is also a fully contracted. So let's remember what the covariant derivative is. All right. The covariant derivative of a contravariant vector component is the partial derivative of that component plus, because you got contravariant component, you got a plus, this extra term here. Now, to do what we want, which is this, we have to change this j to an I, or that I to j, it doesn't matter. It works the same way. So we got I here and I here, blah, blah, blah. There's no free indexes left. Everything's a summation index. Do you see that? Okay. Now, what are we going to do with this thing? This is the first time I've run into this. This is a contraction of a Christoffel symbol. So let's try it out. How do we evaluate the Christoffel symbol normally? Christoffel symbol, the second kind. All right. So it is the inverse metric tensor times all these derivatives of the metric tensor with respect to components. So let's change this j to an I, like this. So now we got I here. So we only got one free index left, k. So we change that j to an I, that j to an I, and that j to an I. Now, in every textbook and online, everywhere I've found, it says, and it is obvious that these two are equal, thus it's 0. Well, I'm sorry, it's not obvious. It's not obvious to me at all. I had to do an example, okay? This is a double summation, but it still doesn't make it obvious to me. Maybe I'm dumb. All right, so I want to do an example. So let's let k, which is our free index, equal 1. And we want I and m to run from 1 to 2. So just do this in 2 dimensions. So we're going to have a double sum that looks like this. We're going to sum over I and then sum over m minus sum over I and sum over m. All right, so we'll sum over I first. So we put in our k, which is our free index. See it? 1, 1, 1, 1. All right, then everywhere you see an I, the first case is 1, second case is 2, first case is 1, second case is 2. Then we sum over m. So everywhere you see an m, first case is 1, second case is 2, and you get this expression. And sure enough, this is equal to that, and this is equal to that, and this is equal to that, and this is equal to that. So they are the same, equal to 0. Okay, I'm happy. But it wasn't obvious to me. I had to do that. All right, so now we have this expression, and it is obvious that these are equal, so we get rid of them. All right, so what is this? What are we going to do with this? Okay, this is where the secret squirrel formula comes in, and I like to never found this or understand it, but I did. Okay, if we have a matrix A and its determinant of A, Jacobi's formula gives us this. The partial derivative of that determinant with respect to a coordinate is equal to the determinant times the trace of the product of the inverse, the matrix times the partial of that matrix with respect to the coordinate, the same coordinate. Wow. That is one hell of a formula. I'm quite sure I've never seen it before. All right, let's see how it works. I had to do this by hand. All right, so here's our equation. All right, and we're interested in the metric tensor. So I chose the metric tensor for the coordinates, which is 1, 0, 0 r squared. So the inverse metric tensor is just 1, 0, 0, 1 over r squared. All right, so we need the determinant of the metric tensor. So that's r squared, right? Determinant of this. And we need the partial of the determinant of the metric tensor with respect to r, because that's the only coordinate we got. We got r and theta, but there's no thetas anywhere, so there's no point in doing it. Everything would be 0. And 0 always equals 0. So let's see, the partial, so this would be the partial with respect to r is 2r. All right. Now we got this stuff inside here. So what is g, the metric tensor inverse times the partial of the metric tensor with respect to r? All right, so here's the inverse metric tensor. The partial of this with respect to r is 0, 0, 0, 2r. Multiply those together, we get 0, 0, 0, 2 over r. Now we take the trace, which is adding these two, right? So 2 over r plus that, so it's just 2 over r. We got everything we want. Okay, so here, this is 2r. Determinant is r squared. This is 2 over r. So 2 over r times r squared is just 2r. Takes 1 r out, got 2. That's equal to that. So this is equal to that. All right, so that's how it works, and it worked. But I've never seen it before, so I needed to play with it. Okay? Where were we? Okay. So we have this thing, and we're going to use Jacobi's formula. All right? So you can see that this looks very much like this. It's the same thing as this, except for trace. Okay, here's the way this was explained, and I think I understand it. Because this is a full contraction. Now, these metric tensors and its inverse are fully symmetric. So IM is equal to MI. So this is a full contraction, so you don't have to worry about the trace. It's taken care of in that contraction. That's the way it was explained, and I think I understand it, okay? So given that, we're going to call G the determinant of the metric tensor. All right, so using this equation, we've got the partial of G with respect to a coordinate times the determinant right here, determinant times this piece right here, okay? Now, what can we do here? We can take G to the other side, and we got this piece. Now, this is what we had right here, right? So I can substitute in, so this is equal to that, and this is what we had. So we're going to put this right there, and we get this expression. Now, now this is okay, but except we want this expressed in terms of the square root of G. This is called the volume element in general relativity, and that's the way we want to express our divergence equation, okay? So let's look at this. What is the partial derivative of square root of G with respect to a coordinate, all right? So it would be, so this is G to the 1/2, you bring down your 1/1/2, you got G to the 1/2 minus 2 over 2. So that makes it G to the minus 1/2, which is in the denominator. Yes. Then you take the derivative of what's inside. So all I did was differentiate the way you would anything. And this is the expression you get. Okay. Now, we can take this to the other side. And now we have this expression isolated. And we want to put this in right there. Okay. So now it looks like this. So the 2's cancel. We've got a G to the 1/2 times G to the minus 2 over 2, which is going to give us G to the minus 1/2. So it makes it go back into the denominator. And so this is our final expression for the contracted Christoffel, the symbol. Okay. Now, let's go back to where we were before we went on this trip. So we want to put this right back in there, and we get this expression. Now, look at this expression. Everything in here, there's no free indexes. Summation index, summation index, summation index. They're all dummy indexes. And we can name them anything we want. I could call this George if I want to, but I'll change it to I because I got I's everywhere else. Okay. So here, now I can start isolating things. So I can pull out a 1 over G, the square root of G, which means I have to multiply this by square root of G, right? And then this is unchanged because I pulled it out. Now you may recognize this as the differential of a product. All right, so we got 1 over square root of G times the partial of this product differentiated with respect to this arbitrary coordinate. All right, so it'd be the first times root of the second plus the second times root of the first is exactly that expression, right? So that is the generalized expression for the divergence of a vector field in any coordinate system. So it is invariant. Okay, so this is getting too long. Next time we might do some examples of this. All right, thanks for watching. See you later.